Hello everyone, my name is Thomas Elton, and this presentation will cover the muddy card system that I designed to save lecturers time when identifying the most confusing points from their lectures. So before discussing muddy cards, we first have to define active learning. Active learning is any task that involves students in doing things and thinking about the things they are doing. In other words, active learning describes tasks where students are actively doing something. Muddy cards are a type of active learning technique where students record the most confusing, i.e. muddiest, point from a lecture. So let's have a look at the general process for the traditional approach to muddy cards. So students will go to a live lecture, and at the end of a live lecture, students will write down the most confusing points from the lecture. The lecturer then will read the responses and summarize the recurring points. And then there are various ways of addressing the muddy card responses, such as making clarifications in the next lecture or via the course website, as well as making changes for future iterations of the course. In literature, various benefits of muddy cards have been reported. One benefit is that students perceive muddy cards as effective at understanding and achieving a unit's learning outcomes. Another benefit is that muddy cards facilitate an instructor-student dialogue. In a unit where muddy cards were implemented, there was a perception among students that instructors cared for their understanding. Muddy cards lead to an increase in student self-efficacy. And finally, we know that active learning techniques improve memory retention for students, which infers that muddy cards do as well, as they themselves are classified as an active learning technique. While there are many benefits to muddy cards, one of the challenges of implementing them is the time required for a lecturer to read and summarize responses. Indeed, Mastella, who was the first person to implement muddy cards, spent 30 to 45 minutes analyzing student responses. Similarly, when muddy cards were implemented for a 60-student class, one instructor had restricted the time engaging with them to 1 to 1.5 hours. Now, naturally, one might question, how is this going to scale to the large cohort sizes at University of Sydney? For example, the NLP course has around 400 students, and the second year algorithms course has around 1,000. So to resolve this temporal challenge, a few different technological approaches have been proposed. One approach was by King, who used clickers, which is where students are handed a remote with numbered keys to indicate what their muddiest point is from a predefined list, and an example of this is shown on the slide. Now, an issue with this approach is it leads to the loss of the student perspective because students have to stick to a predefined list. They're not able to freely articulate what they're confused by. Another approach is Mudslide, which contains an interface where students would click on lecture slides to spatially pinpoint their muddiest points. So as an example of how Mudslide would work, on the screen at the moment, we have a slide as it would appear in a lecture. And the next image illustrates how Mudslide students have spatially pinpointed their most confusing points. Now, in Mudslide, along with each spatial click, students will provide written explanations of what was confusing. In dense regions with many spatial clicks, there is still going to be that time-consuming process of needing to analyze the written responses. And because of this, newer approaches use natural language processing techniques to understand muddy card responses. Indeed, this is the approach taken by Coursera, a system which semantically clusters muddy card responses, providing a summary to the instructor. So students enter their muddy card responses on their mobile phone, with teachers receiving a summary of the clustered responses. However, in Coursera, the instructor is passive during analysis. We believe that there is value in the instructor being involved in analysis. So with this previous literature in mind, we propose our own muddy card system, which similar to Coursera, also contains a student and a teacher interface. In the student interface, the first step involves students answering the question, what was least clear to you in this lecture? In the second step, which we refer to as the student-assisted approach, students are prompted with peer responses that have been deemed similar by the system. They are prompted to select whether these candidate responses are semantically the same to the response that they entered. We're going to use this data to aid the semantic clustering in the teacher interface. So the second part is the teacher interface. And here, student muddy card responses will be embedded and agglomerative clustering used to semantically group responses. Now, as previously mentioned, the data collected through the student-assisted approach will also be used to inform clustering. Now, a key difference here with Course Mirror is that in our system, the instructor is active through analysis. They fine-tune the clusters and the representative quotes. Now that we've described the system, we can explore the related research questions. So the first research question is, how well do sentence embedding models perform when clustering muddy card responses with the student-assisted approach? The second research question is, how do students and teachers perceive the effectiveness of our muddy card system? Let's start with research question 1. So the general approach we use for the embedding benchmarking is to start with a lecture or sample of muddy card responses. I would then manually cluster the muddy card responses into groups of semantic similarity. I'd then use different sentence BERT embedding models and proprietary models from OpenAI and Voyage AI to semantically cluster the muddy card responses using agglomerative clustering. Finally, we would compare the manual and AI clusters using adjusted RAND index, adjusted mutual information score, and SQAS score. So what is SQAS? Well, SQAS stands for Student Question Answered Satisfaction Score, and it is a new metric created for this project to determine the proportion of students satisfied that their question was addressed/answered. Now, to illustrate how the SQAS score works, I'm going to show you a quick example of how to find a SQAS 2 score, where here the 2 indicates an instructor has addressed 2 student muddy card responses. So to find, and sorry, also really quickly, importantly, here on the screen, we have 2 sets of clusters. On the left, we have the algorithm clusters, and these were generated using an embedding model. And on the right, we have the manual clusters, and these are the manual clusters that would have been determined by a researcher. And for a SQAS 2 score, these act as our oracle. So the first step in finding a SQAS 2 score is we find the 2 biggest algorithm clusters. Then we find the medoid of each cluster, which here are the sentences E and G. We then find where E and G lie in the manual clusters. We get the size of each of these manual clusters. Hence here, we have 5 students satisfied that their muddy card was addressed. The SQAS 2 score is then the proportion of satisfied students, which here is 50%. However, what we can see is the best possible SQAS 2 score would have occurred when the 2 biggest manual clusters are accounted for. This would have resulted in a score of 70%. And so here we can see that the algorithm clusters underperform. They're not as similar to the manual clusters. The embedding benchmarking process was repeated for 2 different data sets. First, I manually clustered around 800 muddy card responses across 2 lectures from the 2024 offering of the NLP course. As part of this, I conducted simple hyperparameter tuning to determine the best embedding model and parameters for the initial muddy card system design, so we had a good system for the user study. Then, I manually clustered approximately 1,500 muddy card responses, encompassing 6 samples worth of muddy cards that we collected in the soon-to-be-described user study. My supervisor also manually clustered 2 of the 6 data samples. After adjudication, it was found that my original clusters were not that far from the consensus. We will be releasing the 2025 data to the public as a muddy card clustering benchmark, and also to allow for public scrutiny of our manual clustering. In the results today, we're going to focus on the 2025 data. So on this scatter plot, we're going to plot the adjusted RAND index and SQAS 15 score for each embedding model for different muddy card data samples. As a reminder, SQAS 15 is the proportion of students satisfied after 15 muddy cards are addressed. To start off with, we're going to plot the results for the finance unit's muddy card responses. Here, each point represents a different embedding model. Now we're going to add the performance for all the data samples. So these are the embeddings for each data sample. One thing we can see is that there is a fairly large range when considering the adjusted RAND index for a lecture. And this is also similar when you consider the adjusted mutual information score. This suggests that for these metrics, different embedding models do have a considerable impact on clustering performance. However, when you consider the SQAS 15 scores, we see that there is a much smaller range, indicating that different embedding models do not have as great of an impact on this metric. Now, despite showing consistent SQAS 15 values, we can see that the points are actually quite far from the gold standard as shown here with the finance unit's money card responses. In fact, all of the lectures are generally far from the gold standard values, although some lectures are better than others. This indicates that there is still much room for improvement among embedding models. One way to improve clustering quality is using the data collected from the student-assisted approach. One method we tried is what we call the multi-evidence approach. So as an example of this, consider that a student wrote money card A and identified money cards B and C as similar, and another student wrote money card D and identified money cards A, C, and E as similar. Here, we see that both students identified that A and C are similar, meaning that we have multiple pieces of evidence that these responses are linked. Under the multi-evidence approach, we ensure that A and C are always clustered together. Additionally, we include D because of the temporal ordering of insertion into the database. Another way of thinking about the multi-evidence approach is that we are searching for triangles of links. Now, before illustrating the multi-evidence approach at work, currently on the slide, these are just the embedding performances for 3 lectures of money cards. Now, we show how the clustering performance changes for lecture 1 after incorporating the student-assisted data. As we see, there is not much change for SQAS score despite RAND index decreasing. Now, when we manually inspected this data, we could see that students didn't really understand the student-assisted approach at first. However, after re-explaining it for subsequent lectures, we saw improvements in SQAS score, yet RAND generally decreased or stayed constant. We hope to do further research on this, as we only have a few samples of data with the student-assisted approach, but we do see that the multi-evidence approach seems promising, especially when considering its increased performance for SQAS, which is our metric of choice for money card applications. We'll now move on to the second research question, which investigates the student and teacher perceptions of the effectiveness of our money card system. Now, this research question was explored through a large user study, which encompassed 20 University of Sydney units, including undergraduate and postgraduate classes across 6 faculties, and altogether 10,757 students were enrolled over all these units. One of the main objectives of the user study was to understand the teacher's perceptions of the teacher clustering interface. Now, to establish a point of comparison, we also created a baseline interface with rudimentary sorting features. We chose these features as we believe they are similar to what would be available to someone using the traditional approach to money cards if they were, for example, to place them into a spreadsheet software. To conduct the user study, we used a mixed methods approach, which included a money card response rate analysis, lecture-by-lecture surveys, lecturer interviews, a final lecturer survey, and final student surveys. Let's have a look at some of the results. So the figure on the slide shows the total number of money cards collected, separated by week, and whether money cards were compulsory for a unit or not. Now, when we say compulsory, this means whether money cards were for course credit or not for a particular unit. We can see that overall, there is a really low response rate, and this is even more striking when considering that around 10,000 students were accounted for in the non-compulsory units, compared to the approximately 400 enrolled in the compulsory unit. Only one unit had compulsory money cards, and this was my supervisor's unit. So although we would see some interesting variation here, I'm unable to really explore this because I'm unable to interview my supervisor. Now, interestingly, this low response rate is despite many teachers agreeing to some extent that they regularly remind students to submit their money card responses. Now, in the interviews, I really wanted to dig into this low response rate. And so there were many suggestions that came up through the interviews as to why there was this low response rate. One was just lecture attendance naturally decreases through semester. So if students aren't going to lectures, it's unlikely they're going to fill out a money card. Generally, lecturers identified low engagement when it comes to optional activities. Some people questioned whether our money card system offers unique value over class discussion forums. Some question the relevance of our system when students can just get fast answers using AI. There were some people that raised that because our website was external to the university ecosystem, that this could have hindered the response rate. And finally, there were some isolated cases of low teacher engagement. The interviews asked about teachers' perceptions of the system's effectiveness, Now, unfortunately, for a lot of the cases, this was hindered by the low response rates, meaning teachers did not experience the baseline and clustering interfaces to a large enough extent that allowed them to draw comparisons. That being said, from the data that we did collect, the clustering interface was generally preferred over the baseline interface. Reasons for this is that in the baseline, it was hard to process responses when there are many of them. And additionally, the alphabetical arrangements in the baseline interface were not useful. There was a perception that the clustering interface saved lecturers time, and we have a representative quote for that, which says, "So if there's a technology that will cut out a step for you and save you 10 minutes, then I'm all for it. So I really did like it." In the lecturer interviews, a recurring theme was that students need to see the value in writing muddy cards for the response rate to improve. Now, this notion is partially confirmed when considering the results for the survey question that asked students to rate their agreement with the statement, "Course teachers engaged with the class's muddy card reflections," and the statement, "I benefited from writing muddy cards." Here, we've separated the results by whether muddy cards are compulsory for a unit or not. Among the students in the unit where muddy cards are compulsory, many students strongly agree that the course teachers engaged with the responses. Subsequently, a higher proportion of students in the compulsory unit agreed to benefiting from writing muddy cards. In interviews, teachers stressed the importance of students seeing teachers engage with the muddy cards for an increased response rate. And from this data, we see that students perceive generally lower teacher engagement in the non-compulsory units. Hence, lecturers suggest a future implementation of muddy cards should involve addressing the muddy cards live in class. Currently, the system is designed for an instructor to analyze responses after class, but by addressing responses live, students see the benefits of participation, and there is instant gratification for students as their responses are addressed straight away. If students see the benefits of participating, lecturers believe this will increase the response rate. This raises an interesting avenue for future research. In conclusion, the main contribution of this thesis was developing a system that clusters muddy card responses by semantic similarity. To investigate the best embedding model to use in our system, we benchmarked different embedding models using our purpose-built SQAS metric. To further improve clustering quality, we also implemented the student-assisted approach. We will be releasing the clustered user study muddy card data as a clustering benchmark. And finally, we validated the muddy card system, showing a clear avenue for future research. Thank you, and are there any questions?